Hello, today we're going to talk about wave properties. The objective is that students will be able to recite the equations and properties of waves. Let's get started. So first, let's talk about what a wave is. A wave is defined as a disturbance through which energy can transfer. Some waves require a medium to travel. And a medium is the material that a wave can travel through. For example, sound waves require a medium and usually travel through air to get to our eardrums. So the speakers that you're listening to hear my voice are pushing on the air, and that pushing of the air molecules eventually hit your eardrums, and that's what your brain interprets as sound. This is why sound doesn't work in space. So, because there's no air in space, whenever you see a movie where there's a big space explosion, there's a big boom, you wouldn't actually hear that. There's no sound transmitting through space, because there's no medium for sound waves to travel. There's two main categories of types of waves, physical and electromagnetic. Physical waves, which are also called mechanical waves, are those that require a medium to travel through. Examples are sound waves, like we already talked about. Seismic waves, like from earthquakes, need earth to go through. Heat waves need air or something to transfer the heat through. And think of like the wave at a stadium where people stand up in a row and it makes a wave travel through the stadium. That's the same idea. Without any people there, there'd be no wave. Electromagnetic waves are different from physical or mechanical waves because they do not require a medium. This is why light can travel through space and physical waves can't. There's various types of light waves, and they are radio, microwaves, infrared waves, visible light, that's the stuff we actually see, ultraviolet waves, x-rays, and gamma rays. More on these on another day. But for now, know that these are electromagnetic, they do not require a medium, and all the other types are physical and they do require a wave, or a medium to travel through. There's actually two main types of physical or mechanical waves, transverse and longitudinal, and we're going to talk about transverse first. Transverse waves are those in which the direction of the wave is perpendicular to the displacement of the particles in the medium. In other words, if you look at this picture down here, the wave appears to move to the right as you watch this thing. But if you look at one of the particles, let's say like this one right here by where I'm pointing, it's only moving up and down, up, down. So it's not actually moving left and right, even though it looks like the wave is. So you have the particles moving up and down, the wave moving left and right. Those are perpendicular to each other. That makes this a transverse wave. So let's talk about the parts of a transverse wave. The crest is any maximum point, so any of these up here is a crest. A trough is a minimum, that's at the very bottom. So these are all troughs here that I'm pointing to. A wavelength is any distance from one point on a wave to the same time that next point happens, or the distance between two successive troughs or crests. So this would be a wavelength up here, but you could also go from this trough to this trough. That would be one wavelength. Or this middle point to the next time that middle point happens, which would be over here. So this would be also one wavelength. Equilibrium is the original starting point of the particles in the medium. That's this dotted line in the picture. It's basically the middle point, halfway through the total height of the wave. Amplitude is different than the total height. Amplitude is only the distance from the equilibrium up to a crest, like this little area here, or from the equilibrium line down to a trough, which is the same amount of distance as over here. So the amplitude is actually half of the total wave height. Longitudinal waves are different in that they actually compress the medium. So sound waves are a good example of longitudinal waves. They actually compress air. So the areas here that look very compressed, these spots right here and here, are crests. So the distance between them would be one wavelength. These emptier spaces in between are called troughs on this type of wave. So sound waves are an example of longitudinal waves, and they compress air. So these are often also called compressional waves or compression waves. They move particles of the medium parallel to the direction of wave motion, whereas transverse was perpendicular. So the particles will move left and right, and the wave will also move left and right. Those areas of troughs where the particles are less compressed, those are called rarefactions. That's the opposite of a compression. So if you see the particles in red, like this one right here, this one up here, notice that they're moving left and right. So they move to the left, then they stop, then they move to the right, then they stop, then they keep going back and forth. But if you look at the picture, it looks like the wave is traveling from left to right. So as these particles get compressed and decompressed and compressed and decompressed, making areas of compression and rarefaction, it makes the wave move from left to right, while the particles of the medium are just moving back and forth. They don't get carried along with the wave. Frequency of a wave is defined as the number of waves that pass through a given point each second. Generally speaking, if a wave's moving faster, it has a higher frequency, because more waves will go through the same spot in the same amount of time. The period of a wave is defined as the time it takes for a wave to complete only one cycle. In other words, period is the time it takes for a wave to come back around to the same point on the wave. The speed of any wave is determined by two things, the frequency and its wavelength. And here's the equation, where v is the speed measured in meters per second, f is the frequency measured in hertz, usually abbreviated with hz, and that funky looking symbol stands for wavelength, measured in meters. That funky symbol is lambda, Greek letter lambda. There's another equation we're going to talk about that relates period and frequency. It's a little bit more simple. It's just the period equals 1 over the frequency, where capital T stands for the period of the wave measured in seconds, because it's the time it takes to finish one cycle, and frequency is f, and that's measured in hertz. So according to this equation, period and frequency are inversely proportional to each other, meaning that as one goes up, the other must go down. So they're always going to do the opposite of each other. The last thing we're going to talk about in this video is superposition of waves, otherwise called interference. Any two waves that cross each other can interact and cause an interference. There's two main types of interference, constructive and destructive. Constructive interference is when the waves combine to make bigger waves, and destructive is when they combine to make smaller waves or cancel each other out. Here's an example of constructive interference. So if these two wave pulses are moving on a medium toward each other, when they meet, since they're both above the line, they would meet and make an even bigger wave. Then as they move away from each other, they go back to their original size. So they only make constructive interference at the moment they completely overlap. If they're on the bottom side of the medium, it would still do the same thing, just on the bottom. Destructive interference, on the other hand, produces smaller waves. So if this one were on the top and this wave pulse was on the bottom, at this point here, when they perfectly overlap, they would completely cancel each other out. So this is just, you're imagining what they are. They're exactly the same size on top and bottom. There would be nothing there. It would just be a flat string. And then after they move away from each other, they go back to their original size. This can be also true if you have two pulses of different sizes. Like this one's bigger than this other one, but they're still on opposite sides. So they'll kind of subtract together. Since the one on the left is originally bigger, you end up with a little wave pulse above the line. Then once they move away from each other, they're back to their normal selves again. That's it for this video. Thanks for watching, and remember to bring your notes with you to class next time to help you on the note quiz. See you next time.